Lasers, a solution seeking a problem. Lasers can be found in lots of everyday technologies, most of which I'm assuming you've already experienced, so be it CD players, your optical mouse, or even supermarket self-checkout scanners. Since lasers' inception in 1958, they've become much more efficient and very much easier to use. But what distinguishes a laser beam from, say, the beam of a flashlight or a light bulb even? So the main difference is that lasers possess three specific characteristics, these being that laser light is monochromatic, coherent and directional. As you can see the difference between the thermal light source there in the diagram on the left and the laser light on the bottom left. So what do these words even mean? So monochromatic light is that the light released contains one specific wavelength or one specific color. As you can see in diagrams B and C on the top left, all light emitted there is green, or it is the same wavelength. So coherent light is light that is organized, or that each photon moves in step with all the others. So as you can see in the bottom left there, the coherent light wave pattern, all the peaks and troughs line up nicely, whereas the incoherent, it's all a bit chaotic, there's no kind of nice lining up of peaks and troughs. Finally, directional light is light that is very tight, a tight beam, and is very strong and concentrated. So as you can see, the difference between light sources B and C in the top left is that B is quite divergent, whereas C is very nice and directional. So moving on, what is the underlying physical process that drives laser light, or the production of light that contains these three characteristics? And the short answer is stimulated emission. So stimulated emission occurs when a photon is incident on an electron in an excited state, so a state that is of higher energy than its ground state, and when the photon interacts with this electron, it will cause the electron to fall to the lower energy state, and when this occurs, the electron will release a photon of the same energy, phase, and direction as the incident photon. Now this process is a bit different to the spontaneous emission, as you can see down the bottom left, where there is no incident photon and the photon produced by the electron is of random direction and phase. So now that we know the underlying physical process and the three properties that this produces, how can we induce this in our own lasers? So this is done by the process of pumping. So pumping provides the system with energy, so it allows the electrons to jump to these higher energy states. So pumping is usually done by a light or a current provided to the system. So when the lasing condition is met, the laser will produce lots of photons with the three properties previously discussed, and will eventually produce a beam. So now that we know how we can induce this in a sample, how do we increase the power output? So to do this, we create a cascading reaction by surrounding the sample with two mirrors. So as you can see in the GIF on the top left, the photons will bounce forward and back between the two lasers, and between two mirrors, and the mirror on the right will allow some of the photons to pass through, as it's not totally reflective. So I'd say the mirror on the left would have kind of reflectivity of about 100%, whereas the one on the right would be a small bit less. So as these photons are reflected back into the medium, they can interact with more electrons in the excited state and produce more photons, which then in itself will create the cascading reaction. And as you can see in the bottom left, an equilibrium state will eventually be reached when it'll just be a constant output of photons. And that is how lasers work.